According to the remediation process, once the risk for human health and environment have been identified, suitable remedial measures have to be applied to satisfy the defined acceptable risk level. Radiochemists help to design barriers which would prevent uncontrolled radionuclide releases into environment. To this purpose, radiochemists perform diffusion and sorption experiments of different radionuclides in contact with different potential barrier materials. Concrete and clay are the most studied materials for barriers. These materials will potentially be used to design long-term disposal sites for the safe disposal of long-lived radionuclides from spent nuclear fuel. They are also used for the remediation of waste sites with elevated natural radionuclides such as past uranium mining, phosphogypsum waste, or xenon from the oil and gas industries. The phenomena of sorption and diffusion have to be taken into account when designing a barrier. Sorption is a physico-chemical process where radionuclides attach to solid particles from liquid solutions. Sorption processes slow down or completely stop the radionuclides movement in the environment. Typical sorption experiments consist of mixing the radionuclide of interest with a slurry of sorption material for a specified amount of time, which can be up to several months, and evaluating the amount of radionuclide left in the solution. Radionuclides of interest could include cesium-137, plutonium-239, americium-241, carbon-14, or uranium-238. Sorption properties of a material are characterized by the distribution coefficients Kd, which is the concentration of the radionuclide in the solid phase divided by its concentration in the liquid phase. On the other side, diffusion is the net movement of molecules from a region of higher concentration to a region of lower concentration. Diffusion is driven by a gradient in chemical potential of the diffusing species. Diffusion is a passive process by which radionuclides can move through a barrier. It is usually rather slow, but as risk from high radionuclides concentration will be present for centuries, it may become significant. Typical diffusion experiments consist of barrier which is contacted from one site with elevated radionuclide concentration and left over time. Then the penetration of radionuclides through the barrier is evaluated by observing the concentration gradient from outer surface to inner material. Another possibility is to immobilize the radionuclide in a suitable matrix to avoid its spread in the biosphere. Vitrification is one of the most suitable waste stabilization procedures for aqueous radioactive wastes, which should be solidified before safe disposal. Vitrification is a process of forming glass at high temperature from a mixture of wastes and additives. Glass is an amorphous material which is highly chemically resistant, which allows it to remain stable in corrosive environments for thousands or even millions of years. Incorporating wastes into glass ensures a high degree of environmental protection. Radioactive waste vitrification is attractive because glass has a high capability to immobilize a range of radionuclides, it has a simple production technology, and the resulting waste form has a small volume, high chemical durability, and high tolerance to radiation damage. Radiochemists apply the vitrification process to high-level radioactive waste as well as to low and intermediate-level radioactive waste. In the vitrification process, glass-forming additives are mixed with concentrated liquid wastes, and the glass-forming batch is produced in the form of a paste. This is then fed into the melter, where water evaporation occurs, followed by calcination and glass melting. Melted glass is then poured into containers and cooled down. Elevated levels of natural radionuclides, which can increase radiation risk, can be present in drinking water. This is the case of water abstracted from groundwater sources containing higher levels of natural radionuclides. Radiochemists help to design treatment procedures aiming to reduce natural radionuclide content in drinking water. Among the most efficient treatment procedures are those based on the ion exchange, granular activated carbon, and nanofiltration. Ion exchange is a process that allows the separation of ions and polar molecules based on their affinity to the ion exchanger. Anion exchange resins can be used for the removal of uranium and polonium-210, while cation exchange resins can be used to remove radium-226, radium-228, and lead-210. Removal of polonium and lead is merely a side effect, as they are particle reactive and are trapped in ion exchange columns as particulate matter and not as part of the ion exchange process. Granular activated carbon absorbs contaminants from the water by trapping them inside the pore structure of the carbon substrate. It is the most efficient method for radon removal, though it is not very suitable for other natural radionuclides. One efficient measure to remove radon is aeration, as radon is noble gas dissolved in water. Nanofiltration is a process based on the use of membrane filters with a selected molecular cutoff to remove larger molecules from the feed water. It can be efficient for uranium, as uranyl complexes predominantly found in water are usually larger than the typical molecular cutoff size of nanofiltration membranes. All these methods reduce risks from radionuclides in drinking water. At the same time, radionuclides are concentrated in regenerating solutions for ion exchangers, activated carbon, and retentate, which is material retained by filtration units. This becomes radioactive waste and has to be treated and disposed of accordingly. Radiochemists have an indispensable role in the process of designing efficient remedial measures to achieve the desired reduction of radiation risks to which we are exposed.